But when you start, you just press it when you start, but it's not. You will see a yellow lamp at 4 minutes before the end of your talk. All right. Please have a seat. The session will start in a few seconds. Welcome everybody to the VR and AR technical paper session. My name is Tammy Boubecker from Adobe, and we have 5 papers today, starting with the first paper, Surface Brush from Reality Drawing to Manifold Surfaces. The authors are Enrique Rosales from the University of British Columbia, Yafed Rodriguez from the University of Panamericana, and Ala Schaefer from the University of British Columbia. And this is Enrique and Yafed who will present the paper.
Thank you for the introduction, and welcome everybody to our talk. Drawing provides a natural way for people to communicate shapes. Thanks to virtual reality technologies, we now have the option to not draw only on flat surfaces, but directly in 3D space. Existing VR tools enable users to draw ribbon-like brushstrokes by moving a handheld controller. Artists frequently use dense collections of such brushstrokes to describe complex freeform 3D geometries. Observers can immediately identify the shapes artists describe using this drawing approach. Using such drawings as input for 3D modeling can sidestep many of the challenges present in existing modeling systems. Traditional approaches for 3D modeling or sculpting require a steep learning curve and significant time to create even simple freeform shapes. Existing sketch-based modeling tools can convert 2D sketches into models. However, they have limited scope and rely on domain-specific cues and strict drawing conventions to extrapolate 3D information from 2D sketches. While a range of VR modeling tools exist, most reuse similar paradigms to those of traditional modeling tools, and they typically require a similarly steep learning curve. On the other hand, surfacing based on 3D curve networks requires connectivity annotation and to follow strict conventions. Primitive-based methods such as those operating on basic volumetric blocks are very easy to use, but have very limited output scope. Swept surface-based approaches are more general, but describing a complex shape using a collection of swept surfaces requires a high degree of expertise. Using VR brush drawing as modeling input provides an appealing alternative to all these methods. Using this interface, even novice users can easily produce compelling freeform shapes without following explicit drawing conventions or utilizing clunky interfaces. The question we need to address is how to convert these drawings into 3D models. Before discussing how we can do this, let's analyze the properties of these drawings. This is how a typical completed drawing looks in VR environment. A dense collection of root surface brushstrokes that look like ribbons. Users can control the width of the ribbons and set their tangent plane orientation by moving the control handle. Internally, VR systems represent each ribbon using its central polyline and its respective width. The ribbon polyline information includes both vertex positions and normals. For simplicity, from now on, I will use the term stroke to refer to the central polyline. Ribbon rendering is double-sided. Thus, viewers are oblivious to normal orientation. However, once we visualize normal orientation using different colors, green for front and turquoise for back-facing ribbons, we observe an important phenomenon. Normal orientation is highly inconsistent and frequently changes between adjacent strokes. This inconsistency is persistent across artists and inputs. Approximately 1/3 of the strokes in each of our inputs are oriented in the opposite direction to the plurality. Double-sided rendering implies that users are not aware of ribbon normals, so they change controller orientation to maximize access convenience. On this example, we can see that the artist is drawing the ribbon from outside. However, when drawing this other ribbon, instead of walking around the horse, he draws the ribbon from inside. Another important phenomenon we observe when analyzing this data is the prevalence of strokes extended into the interior of the models. Specifically, artists are only interested in how the shapes look from outside, and often extend strokes into the object's interior, producing multiple intersecting stroke groups. Given these characteristics of the inputs, how can we convert them into 3D models? Notably, the majority of geometry processing algorithms and downstream applications require manifold meshes. Therefore, our goal is not to create any model, but to create a manifold mesh and to leave as few holes as possible. So how do we construct the desired output from this input? Recall that our recorded input consists of ribbons described using a central stroke. One very simple idea would be to use the stroke's vertices as input for traditional reconstruction methods from point clouds. Unfortunately, both methods, which rely on positions only, as well as methods which rely on position and normals, fail dramatically on this data. Here's another alternative. Since we have ribbons, how about densely sampling these ribbons and using these samples as inputs? Sadly, all the methods we tested fail on this data as well. Here's another idea. What if we can directly use the triangulated ribbons as input to polygon sub-repair methods? The results are similarly bad. In conclusion, we need a new dedicated modeling method. The input to our method consists of the core data recorded by the brushstroke interface, the positions, the normals of the stroke vertices, and the ribbon widths. Notably, when we look at our data, most stroke vertex positions and normals up to orientation are fairly accurate. Hence, we want to use these vertices as the backbone of our output mesh. We hence can cast our reconstruction goal as identifying and connecting vertices which are expected to be adjacent to the output surface. We refer to vertices we seek to connect as matching. Also, our algorithm or framework must account for outlier or off-surface vertices as well. So, what kind of matches do we want? We want our matches to induce manifold mesh, and we want them to be perceptually correct. This means that we typically want to connect consecutive stroke vertices. What about matches across strokes? We know that we want to connect vertices which are proximate and normal compatible. However, given the limited success of the previous methods, we know that these priors are not sufficient. We need additional perceptual cues. So let's look again to the data. Look at the vertices which we are expecting to be adjacent. They very often have similar stroke tangents. Often is not always. We can have vertices which are close by and we might want to connect them, whose tangents do not match. These observations suggest using a stroke tangent similarity as a vertex matching cue in addition to proximity and normal consistency. Here's an even more important observation. Consecutive vertices along a stroke are very likely to perceptually match to similarly consecutive vertices or on the same vertex. We refer to this property as persistence. Notably, perceptually best matches can connect vertices on different strokes or on the same stroke. Of course, we have exceptions to this rule. However, in general, we expect most matches to be persistent, forming long matching strong sections. Persistent expected adjacency implies persistent matches. Thus, we expect perceptually correct matching to match between vertex sequences. We are a sequence of series of consecutive vertices along strokes. Therefore, we expect to have sequence of consecutive stroke vertices to match to another sequence of consecutive vertices. And note that the matches should not necessarily be bijective, because a stroke section can have different vertex density. Given those matches, we can form the output surface by creating surface strips bounded by the matched stroke sections. Performing this process for all matched sections, we can obtain a collection of interstroke strips that define the intended surface up to a few gaps and holes. We could then complete the mesh by closing the gaps using a similar framework connecting sections of those gaps borders. Overall, Our algorithm looks as follows. We first create a collection of interstroke strips. We then close the gaps to generate a final manifold surface. In this talk, we will focus on the first part. Let's now look at the core of our algorithm, the matching process. We know that the matching vertices need to be proximate and have consistent normals and tangents. However, using these local cues alone can produce highly fragmented section-to-section matches. In contrast, by accounting for persistence, we can drastically improve the correspondences, forming lone match sections. We surface the input by forming triangle strips that connect these match sections or vertex sequences. While our use of persistence Q reduces the likelihood of non-manifold matches, it does not prevent them completely. So we need to explicitly enforce the manifoldness requirement, constraining each section to be bound at most 2 strips. Our goal can therefore be formulated as locating adjacent normal and tangent consistent stroke vertex sequences, while enforcing manifoldness constraints by forcing vertices to be inside at most 1 left and 1 right match sequence. Combining these 2 requirements produce an NP-complete problem. We efficiently obtain a suitable solution by locating desirable matches without strictly enforcing manifoldness. We use these matches to form mesh strips. Predictably, the resulting mesh has some non-manifold artifacts. We then detect and resolve any non-manifold artifact by removing a subset of the mesh triangles. The result is guaranteed to be manifold. Let's look at the relaxed matching step in more detail. Our core idea is to locate best matches for each stroke independently, without explicitly enforcing consistency between matches generated for different strokes. For each vertex, we look for the best left and right matches. The output of this process is a union of per stroke matches. These matches are not guaranteed to be symmetric, but in practice, due to our choice of matching criterion, most matches are symmetric. Consequently, the majority of the matches actually satisfy the manifold constraint. The goal of the one-sided matching is to locate the best left and right matches for all vertices along a given stroke. We assess the quality of the matches by measuring 2 scores. Vertex-to-vertex match quality, which accounts for proximity, normal, and tangent compatibility, and persistent matching score that encourages sequence-to-sequence matches. The combined score is formulated as the product of these 2 components across all stroke vertices. Computing the matches that optimize the score amounts for solving a classical Markov chain problem. We compute these optimal matches in polynomial time using the classical Viterbi algorithm. Our vertex-to-vertex match quality score accounts for the following 3 terms. Proximity, measured as the distance between the vertices. Tangent compatibility, measured by assessing the alignment between the tangents at the 2 vertices and the direction of the vector that connects them. And finally, normal compatibility, measured by assessing the degree of alignment between the 2 tangent planes as explained in the paper. Rather than measuring persistence using a topological metric, which looks at the topological adjacencies between pairs of vertices, we measure it by using a geometric metric which seamlessly counts for 3 configurations. The default scenario where 2 consecutive vertices match to similarly consecutive vertices. The scenario where 2 vertices should indeed match the same vertex. And finally, the case with 2 consecutive vertices should match non-consecutive vertices. We use the output result of the matching to form a triangle strips, and note that this output is almost manifold. Here are all the non-manifold edges and vertices produced by this process. Notice that these artifacts are highly isolated. We eliminated these artifacts by removing a subset of triangles next to the non-manifold edges and vertices. Our goal is to minimize the number of triangles removed and maximize the quality of the retained matches. We cast the computation of this optimal output as correlation clustering problem. The exciting details of the formulation are in the paper. The output of this step is guaranteed to be manifold. Once these strips are computed, we complete the process by closing the gaps. We use a similar framework to connect sections on the gaps borders, as detailed in the paper. Jafet Rodriguez will now present the results and validation.
Thank you. To validate our problem statement and algorithm, let's look at more inputs and outputs. We confirm our drawing analysis by an observational study. We asked 5 first-time users to describe 2 simple forms, cube and hemisphere. We did not provide any specific instructions, but we asked them to draw the shape as cleanly as possible. Although they use different patterns to describe the same surface, they all naturally converge to a drawing style that we have observed. Here are our results on this data. In the second part of the study, we asked amateur users to draw freeform shapes, again, as cleanly as possible. The users were able to create interesting shapes with no training and within a small amount of time. Generating these shapes using traditional tools would have required significant training, and it would be a much longer process. More importantly, all drawings exhibit the noted characteristics. Here are the results of our algorithm on this data. We also examine inputs from popular online repositories. These drawings exhibit the same patterns we have observed, and our method can robustly handle those. The ability to create a manifold mesh from these drawings enables us to subsequently process the resulting model. Here, we texturize the resulting surfaces. Our method's ability to output manifold objects is critical for downstream applications such as 3D printing. If the artist generates the drawing as a collection of multiple connected components, our method naturally preserves the component structure without any additional annotation, allowing the artist to easily modify and animate their output models. An interesting feature we notice in the data is that artists often use individual strokes to depict narrow features. Our framework can be adapted to handle this data with minimal changes. Here are some more interesting inputs created by expert artists and our outputs. The walking teapot we have seen earlier. And of course, we had to try the Stanford bunny. We couldn't resist. This model is probably the most complex and time-consuming model of the ones we tested. It required the artist 37 minutes of drawing. Experts are likely to require at least double this time to create similar models using traditional modeling applications. And our algorithm took 8 seconds to compute the manifold results. To conclude, we presented a novel modeling framework that uses VR brush strokes as input. The method is based on an extensive analysis of notable characteristics of such drawings. Our modeling framework is supported by a new algorithm that converts these drawings into manifold user-intended surfaces. Thank you so much for your attention, and now our co-author is happy to answer your questions.
Thank you very much. All right, do we have questions? Please step up to the mic and state your name and affiliation before asking the question. I'm going to start with a simple one. Of course, the structure of the stroke remains in the final surface, and filtering that out might not be trivial. Did you look into getting a very smooth output?
Yes. So, I mean, you can obviously remesh it. That's the one big advantage of having a manifold surface, that now every processing pipeline you have can be used on it. So you can remesh, you can resample, you can also do a whole bunch of topological operations. The interesting question, maybe sort of just slightly diverging, is understanding what kind of smoothing you want. So, I mean, if you want to think about how to smooth this data, you may again want to look carefully at the artist data, because I think there are different modalities of smoothing here rather than, again, generic reconstruction frameworks, because the noise is a different noise.
All right.
Hi, my name is Sydney. My question is, could this be applied to, because in Quill and stuff, you can animate. Is it realistic to apply this correction to an animated file?
Yeah, absolutely. I talk to people who actually work in that space. Yes, because basically what we are giving you to a degree is a grouping of the strokes. So it will enable you to animate groups rather than trying to keep, manually try and pick them. You basically get the connected components, which is usually things which the artist indeed intended to get together. So you can absolutely use it for animation, yes.
So it sounds like what you're describing is animating after you apply the...
You can do both. So in our workflow, just from a coding simplicity perspective, we looked at complete drawings, but there's absolutely nothing inherently in the algorithm which prevents it from doing this as the artist draws, because we can identify when the strokes indeed are likely to be adjacent. So you can use that, I would say, on the fly probably, yeah.
Okay, all right, thank you very much.
Do we have other question? I have a simple one. This is currently a post process. Would it make sense to have it dynamically running on the fly when you paint?
I think you can do it. I mean, I think you probably don't want to do it from your first stroke, because the first stroke still doesn't have enough information. But given how long it takes people to draw, I mean, kind of the disparity in the time is, let's say, 20 minutes of drawing versus 5 seconds of reconstruction. You can definitely do the reconstruction on the fly and then correct it. So you can kind of see what you're creating as you go.
All right, let's thank the speakers again. Yeah, you can go. Okay, the next paper is entitled Perceptual Rasterization for Head-Mounted Display Image Synthesis. The authors are Sebastian Friston from University College London, Tobias Ritschel from UCL as well, and Anthony Steed from UCL as well. And this is Sebastian who will give the talk.
Thank you. Good afternoon. It's a pleasure to be here today to present our work on perceptual rasterization on behalf of my co-authors, Tobias Ritschel and Anthony Steed. When we are engaged with the world, we are not just passively receiving stimuli. Rather, to interact, we form an internal model that generates expectations based on our experiences from the real world. We then act based on this model and see our predictions realized. This is known as the sensory-motor loop. Now, virtual reality is interesting because it promises that by completely replacing the real world, we can build interfaces with little or no abstraction for problem-solving, exploration, and recreation. But due to the expectations in the sensory-motor loop, we must make sure that any generated stimuli accurately matches what would be reproduced by an equivalent real world. If we get this wrong, it results in a number of negative side effects, including reduced performance, motion sickness, and even negative training. And two significant ways that the generated stimuli can differ are in terms of resolution and latency. So the human visual system is less of a passive high-resolution camera and more like a periscope that is constantly interrogating the world around it. The eye has only a few degrees in which it can actually see with high resolution, roughly equivalent to the width of the thumb held at arm's length. Now, this presents a challenge for rendering because it can see in this region with high resolution, but also an opportunity, because we only need to generate high-resolution stimuli in that small area at any given point in time. And the other difference is latency. The expectations that we have about the response of the world are not just in the nature of the responses, but in their timings too. We generate our expectations based on our experiences from the real world. And the real world has no latency. But in practice, in virtuality, it takes a long time, relatively long time, for the computer to compute and deliver
the virtual stimuli to us. So in the common real-time graphics pipeline, images are sampled for a fixed point in time, projected linearly to a buffer of uniform resolution, and scanned sequentially to a display. And this is true of modern HMDs. While there are some exceptions, the majority of HMDs use miniaturized high-density versions of the same technologies that we find in desktop monitors and projectors. And this introduces some complications given our requirements of latency and resolution. Now, our technique challenges some of these assumptions, and to see why, I hope you will bear with me while we do a brief review of some considerations in rendering for VR. So the first issue is resolution. To achieve a high resolution in one area of the display, we must render with that resolution everywhere. And this results in significant computational requirements for the GPU. Second, because the scan-out is sequential, it takes an entire frame period before a given pixel can be updated. It doesn't matter how fast your GPU is, you can never redraw a pixel with a period any less than the scan-out of the entire display, placing a lower bound on latency. Further, the latency isn't constant. Because the scan-out always begins in the same place, a frame is more out of date at the end of a scan-out than it is at the beginning. And finally, head-mounted displays use lenses to optically wrap a relatively small display around the user's entire field of view. The image is rendered for the natural field of view and then transformed with the inverse lens distortion before being scanned to the display. And this introduces the requirement for a distortion pass and also a synchronization stage. So a number of concessions have been developed or leveraged to improve rendering for VR. And one such development is that of low persistence displays. It takes a long time to change the color of a pixel from the color of the previous frame to the next, which on a display with a constant backlight can introduce blurring, like you can see in this video of this high-speed video of an LCD display showing this shrinking sphere. By reducing the amount of time the backlight is illuminated, we can reduce how long users see out-of-date pixels. And this has given rise to different shutter types, analogous to the shutter of a camera, but for the backlight. And one of these is the rolling scan display, such as that used in the Oculus DK2, which you can also see in another high-speed capture here. In a rolling display, different regions of the display are illuminated at different points in time in a rolling band. Rolling shutter displays behave similarly to older CRT displays and laser scanning displays. This type of shutter illustrates how the sequential scan-out presents a challenge for VR in terms of latency, but also an opportunity, because the scan-out creates an interdependency between real-world time and the location on the display at which data is or is not visible. And we can use this to overcome the lower bound due to scan-out if we can figure out how to take advantage of it. So in rendering for VR, we also have a number of complementary techniques, such as prediction. So we'll never actually achieve zero latency, right, because computation takes a non-zero amount of time. But because users move somewhat predictably due to inherent biophysical limits, we can guess where a user will be looking at some point in the future and render for that point when they will actually see the image. Now, prediction allows some compensation of rendering latency, but in the current pipeline, each pixel is generated for a fixed point in time, so it can't account for change in position during scan-out. Another contributing technology is that of image warping. Warping deforms an image so that it appears to be viewed from a slightly different perspective. This could be used to make last-minute changes, reducing perceptual latency further, or even generating in-between frames, reducing the total computational cost over time. Warping in image space, however, has limits that parallel those of simple predictors. Basically, the further ahead in time I look, the larger the warp, the more missing information there is. And in this case, I mean literally missing, because the biggest issue with image warping are disocclusion artifacts. So sometimes warping is used because the graphics card can't keep up. And as displays increase in resolution, this is only going to become worse. With foveated rendering, we can combine an eye tracker with the rendering system to generate high-resolution stimuli only where the user is looking at a given point in time. The foveal function, however, is highly nonlinear, and current pipelines are not designed to sample nonlinearly or perform random updates. So, we have seen some of the challenges for near-eye displays, and I'll now introduce our solution in the form of perceptual rasterization. It is assumed in the current pipeline that the relationship between the buffer location and the sampling location in the world is linear and time is fixed. To support low latency and foveated rendering, we would like to compute each pixel with a more independent, flexible parameterization in time and space, and we refer to the result of this computation as the Foveal Buffer. Now, the Foveal Buffer doesn't have to be used for foveated rendering. It's simply a term we give to a traditional uniform render texture, but for which the location in the texture and the sampling location in the world, that relationship is nonlinear. For example, we could implement the foveation function to dedicate more pixels to the foveal region. We could change the sampling time, so we render an image based on when a pixel will become visible on a rolling scan display. Or we could directly render the inverse distortion of HMD lenses or a composition of all the above. Now, once the foveal buffer has been constructed, we could then resample that if necessary for a particular display. For example, we could unfoveate a foveated image for a traditional uniform desktop display, but now for which we have effectively supersampled the foveal region. To render the foveal buffer, however, we must distribute primitives across it non-linearly. Now, there's already a rendering algorithm out there that supports this out of the box, ray tracing, but ray tracing is too slow to generate real-time images on its own. Ray tracing is just a double loop. The outer loop iterates over all pixels, and the inner loop iterates over all primitives, and for each pair we perform an intersection test. Rasterization is not that different. We just swap the order of the loops. Of course, that way of writing it is highly inefficient. To make it more efficient, we test only the ray primitive pairs that have a good chance of intersecting. For ray tracing, this might be done with an acceleration structure, such as a bounding volume hierarchy. And while these have come a very long way, they're typically still too slow for large, complex dynamic scenes. For rasterization, the culling of the pixels is performed by the fill stage. Now, you might not imagine a fragment shader instance as a ray primitive pair, but that's effectively what it is. It's just we never represented it like that before, because up until now it's always been assumed that the ray parameters are fixed. Now, determining the affected pixels in the fill stage is a process of bounding. Assuming the ray parameters are fixed allows us to use specific types of bounding, such as standard bounding boxes. Bounds are considered more efficient the larger the number of pixels in the bound contributes to the final primitive or composition. And so the least amount of computation time is wasted. In perceptual rasterization, primitives are projected non-linearly into the foveal buffer, and this results in the curved primitives which you see here. And for these, we need to develop efficient bounds. We might assume, for example, that all pixels are affected, which would work, but would be highly inefficient. We could also use these standard bounding boxes, but you can see that they are less efficient than the bounds would be for the equivalent straight-edge primitive. A primary contribution of our work is to derive tight bounds for our perceptualized primitives. To do this, we first connect all vertices, this is all done in image space, to get their edges, and then recover their normals in 2D. We then use numerical techniques to find the offset along the edges, the maximum offset along the edges for any given perceptualization. And then we offset the edges by that distance. We connect the ends of the edges to form a polygon. Now, in practice, we do this by computing the bounds in the geometry shader. We deliver the geometry and model view transform matrices as normal, except in this case, they're parameterized in some way. For example, we may deliver a pair of transform matrices, and perhaps even geometry, one at the start of the frame and one at the predicted pose at the end of the frame, for which we can interpolate between. These space-time transforms are passed through the vertex shader onto the geometry shader, where the bounds are computed in the way we have just seen. The bounds are sent as triangles to the fill stage, which operates in the Foveal Buffer. For the shading stage in the Foveal Buffer, the location in the buffer determines the sampling parameters. These parameters are used to evaluate the space-time transforms and possibly geometry, turning them into traditional primitives. And then we perform a geometric ray primitive intersection and write the result into the buffer. So we evaluated our technique using a number of different criteria. For example, we compared the foveal region of an image rendered by our method to a common rasterization and a ray-traced reference. We also generated images for rolling displays, and we demonstrated that our rolling images could avoid the disocclusion artifacts introduced by warping a traditional rasterization. We analyzed a number of different perceptualizations, including rolling, foveation, and a composition thereof, for a number of different scenes in terms of time, error, and compared our results to alternative foveation methods and ray-traced ground truth. So we'll refer you to the paper for full details, but to summarize a few key points. We had the lowest error of any technique, and our rolling results were bit identical to ray-traced ground truth. We're not always faster, for sure, though we do sometimes outperform multipath methods to foveation and sometimes warping as well. And we do demonstrate the importance of our bounds. Our tight perceptual bounds were significantly, by orders of magnitude, faster than simple bounds such as bounding boxes. Finally, we conducted a number of user studies into the perception of our perceptually rasterized images. We built a working foveated rendering system and demonstrated that we could render non-trivially foveated images which were indistinguishable from commonly rasterized reference images. In a second experiment, we showed that users considered our resampled foveated images to be closer to naively supersampled images compared to commonly rasterized images rasterized at the base resolution of the Foveal Buffer. And finally, using an Oculus DK2 with a rolling display, we demonstrated that our images generated with nonlinear time could significantly alter the bias of the user's head rotation in an object tracking task. So to help explain further, we have produced a small website with a number of interactive widgets that go into more detail about the issues in near-eye displays and our solution in the form of perceptual rasterization that we hope you can take the time to visit. So to conclude, near-eye displays completely subsume the user's field of view, and in doing so, take on the responsibility of generating stimuli that accurately matches the expectations of the human visual system. This includes low latencies and high resolutions. These are challenging to achieve with uniform sampling, but are tractable with non-uniform sampling. Despite us having an ideal non-uniform sampling method, modern GPUs are not designed for non-uniform sampling or scan-out. However, by reframing the problem of rasterization, we can perform ray tracing in the fragment shader, getting some of the benefits of traditional rasterization and ray tracing in one without needing any special hardware. I thank you very much for your attention today, and I hope you will have time to visit our website.
Thank you very much. Do we have questions? Let me start maybe a quick question about the comparison that you showed with dense point sampling. So can you tell us a little bit more how you generate the point sampling to which you compare your technique in one of the slides where you had also the reference image with generated by ray tracing? This one.
This one. So the image on the left is illustration. So that just shows the foveal region that we zoom into with the three images on the right. Our method non-linearly samples that actual 3D geometric scene. And so if you were to look at the foveal buffer, you would see that foveal region blown up slightly, and then we would resample to a traditional display for which we zoom in there. The ray traced reference is is effectively sampling the same geometric scene with the ray parameters that we would use in our method for the foveal sampling.
Okay. Yeah. Yes, please go ahead.
Hi, Kevin Figueroa. Great work, very insightful.
Thank you.
Did you guys try different techniques of, I guess, attenuating the backlight? It looked like you were doing a rolling system. Did you try strobing or addressing the source of the light directly behind the foveated region and then spreading out?
No, we didn't. We would love to do some work on if we had a display for which we could manipulate the backlight in completely random ways. That would be fantastic. We might try to build one actually, but no, that was just one of that particular demonstration was done on the Oculus DK2's display, which only had that specific rolling scan-out pattern.
Do you think it would make a difference?
So for latency reduction, it's important that the rolling scan-out proceeds not necessarily linearly, but proceeds progressively in that manner, because you want that interdependency between time and space. But certainly other types of backlight illumination pattern will have different effects and allow you to leverage them in different ways. Thank you.
One quick extra question, yeah, please.
We used to joke that if the eye or the retina didn't compress the incoming data, the optic nerve would have to be bigger than your head in cross-section. And so the retina has the high resolution sensors in the center with motion detectors out here in the periphery, because from a survival standpoint, I want to update when something moves over here that might, be a predator or something like that. The question is, are we getting close to a point where the GPUs and so forth are fast enough? This is kind of a related, I need to read your paper to fully understand the foveation, but you could predict where the update needs to come from in the periphery, perhaps, and thereby get another gain in the foveation.
Yeah, it's an excellent point. In fact, our co-author Anthony has an experiment that he's been wanting somebody to run for quite a while, where you slightly predict the motion of objects in the periphery, and you warp them in such a way that they're presented sooner than they would be, to see if you can get somebody to respond faster in, say, an object intersection or shooting task. And I personally think it would work, and now I've said it out loud on camera, he's going to have to do it.
It's kind of like bandwidth matching, because you've got all this compression in the retina, and then we're presenting all this huge amount of data out here in the periphery that really is just not being utilized unless you happen to look at that. If you know that it's like an impedance match. It's a bandwidth match of the two, the sender and the receptors. Thanks.
Thank you.
Thank you very much again. The next paper is titled Luminance Contrast Aware Foveated Rendering. The authors are Okan Taran Tursun from Max Planck Institute and Elena Arabazishka from Saarland University. And this is Okan who will give the talk.
Thank you very much for the introduction. Computer graphics has always been striving towards providing greater visual quality. In the past, photorealism was a goal which was infeasible to attain. Developers and animators were simulating real-world graphical effects using higher-level abstractions. Today, we have more sophisticated models, sophisticated lighting effects, such as HDR lighting, subsurface scattering, and even some devices provide the capability for real-time ray tracing. In the near future, we expect the same trend. We will have even more complex models and sophisticated effects. And we will have advanced display technologies. VR and AR are already here, but we expect increasing resolutions such as 4K and 8K. And we expect wider field of view, which bring additional computational demands. In addition, we see novel display formats, such as light fields. A third one which we expect is we see popularity of AI rising, and AI-generated graphics has been recently introduced. Why is this important? Because it introduces additional step of, for example, neural network inference, which wasn't in the rendering pipeline before. If we look at our human visual system, we see that we observe the real world through our photoreceptors at the back of our eyes. However, the photoreceptors are not uniformly distributed. They are concentrated at a narrow region where we are the most sensitive to the visual stimulus. Consequently, we see only a part of the world at one time. We shift our gaze position, and our brains reconstruct a mental image of the visual stimulus. Standard foveated rendering approaches successfully use this aspect of human visual system in order to improve the rendering performance. Günther's and Patni and their colleagues' approaches are some of the notable works. What they are essentially doing is that they are rendering some part of the scene at high quality, provided using the gaze position provided by an eye tracker, and the periphery, they are degrading the rendering quality with increasing eccentricity. Let's see this example. Here we assume that the person is looking at the center, and we have different types of images. If we look at a specific eccentricity, we will see that the foveation is not equally visible for the same amount of eccentricity. So this brings us the following question: how should we degrade the quality in the periphery? Stengel also addresses this problem in their work, but here we focus on luminous contrast. So we know that the visibility of contrast, visibility of quality degradation should depend on both retinal eccentricity and underlying content. In order to address this issue, we propose a predictor which works locally on patches of a frame, together with using other parameters such as retinal eccentricity or the patch, viewing distance, and other display parameters to come up with a resolution map, which guides how much we should degrade the quality in the periphery. So our goals are, the first one is to propose a perceptually inspired model to predict the maximum tolerable foveation. And the second one is to calibrate the model for partial information, because if you make your prediction, if your prediction requires full information of the scene, then you cannot observe any speedups. Our predictor is based on a perceptual contrast model inspired by the human visual system. The first component is band decomposition, because we are not equally sensitive to different frequencies. And it is known that the contrast sensitivity function has a smaller, lower peak value, and the peak value shifts towards lower frequencies. And you can see that these sample images, which have different frequency distributions. In the second component, we are weighting these frequency bands using human contrast sensitivity function, which is also eccentricity dependent. The last component models a concept also known as visual masking. Given a signal, if the signal occurs in isolation, we are more sensitive to the quality degradations to that signal. For example, if we focus on this signal, we will immediately recognize if the signal is absent or removed from our visual field. But if the signal occurs near similar type of visual stimulus, then we are less sensitive to the distortions, and we are more flexible in our quality degradation. So the last component models this type of behavior. And this perceptual contrast model is used in order to compute the perceptual contrast in both full resolution rendering and some amount of degradation introduced by foveation. Our main objective is to keep this loss in perceptual contrast always less than 1. And we are modeling the foveation here using Gaussian filtering, because Albert and Hoffman and their colleagues, they showed that simulating foveation with Gaussian filtering is perceptually equivalent to foveation with proper temporal filtering. One way to solve this is to use an exhaustive type of approach in order to find the optimum sigma, which introduce barely noticeable amount of foveation. But we are introducing a closed form solution which gives us directly the amount of sigma needed for a specific eccentricity and content. For this, we have the following simplification. We assume that the masking due to foveation in spatial domain is not affected too much. So we are able to solve this analytically and come up with a closed form solution for the amount of foveation. Our model has several parameters. Except retinal eccentricity, other parameters has to be calibrated to model human visual system accurately. First one is fundamental eccentricity parameter, which models how fast our visual sensitivity degrades with eccentricity. The second one is contrast sensitivity function. There are contrast sensitivity functions well known in the literature, but due to our decomposition method and leak between the bands, we are also fine-tuning this contrast sensitivity function. And we have 2 parameters to model masking effects. For the calibration, we collect a set of patches, and we need the answer to this question: what is the tolerable amount of quality degradation, which is expressed in terms of sigma, Gaussian filter parameter, depending on content and eccentricity. So we are after having the ground truth, which matches proper sigma with corresponding visual content. A straightforward method for doing this is to conduct a subjective experiment where we place a foveated and full resolution versions of a visual stimulus to a specific eccentricity and ask participants to choose the option which looks sharper. Although this method works, it has two disadvantages. The first one is the number of trials is huge, and it gets infeasible to collect required amount of data. The second one is this visual stimulus occurs in isolation, and it's an unnatural viewing condition because in real viewing scenarios, we rarely see such isolated patches. So instead of this, we take our patch and flip it and cover all the available visual field of view with the patch and apply some level of, aggressiveness level of foveation and ask people if this is visible compared to the full resolution rendering. Using this method, we reduce the amount of trials considerably. So how do we parameterize the foveation aggressiveness? We have essentially two parameters. The first one is radius of foveal region, and the second one is the rate of quality falloff in the periphery. And you can see the effects of changing these parameters, having a smaller radius or larger radius, or having slower fall-off compared to faster fall-off here. We are experimenting with 3 different values of radius and 3 quality fall-off rates. And depending on detection rate of the participants, we label these, each one of piecewise linear lines as not visible or visible. Then we take the not visible ones, which gives us the sigma. So for a given patch, any visual angle on this line gives us the amount of quality degradation that we can introduce to the patch without any disturbing artifacts. We conduct this experiment on 22 participants in 2 alternative force choice manner on 36 patches, and we pick these patches by trying to maximize their frequency characteristics as much as possible. And this gives us, for different visual content, the amount of quality degradation that we can introduce for each eccentricity. So we use this data to calibrate our model. The second goal is calibrating our model for partial information, because as I said, if you have to render a whole scene in full quality, then this doesn't introduce any kind of speedups. We experiment with different downsampling rates and check the mean absolute error for our prediction. And we discovered that using quarter of the resolution provides a nice trade-off between speed and prediction accuracy. So our model provides this resolution map. Here you can see sample resolution maps. We have implementation for static scenes, dynamic scenes, and an application to NVIDIA variable rate shading platform. NVIDIA variable rate shading platform, we have to quantize our resolution map to use their platform. Therefore, we have 2 different outputs here. Now let's see our method in action. So this is the real implementation. You can see the gaze position indicated by this cursor. And this is the resolution map that our predictor provides us with. And this is the quantized version. Oh. Okay, let's try again. So yes, the cursor is showing the mouse, the gaze position. This is the output of our predictor. And we quantize this to available sampling patterns or sampling rates in NVIDIA variable rate shading. And this shows the final rendering. So we evaluate our predictions by asking, again, participants to compare our method with full resolution rendering and pick the one which looks sharper. Since we calibrate our method to 75% of detection rate, we get very close to that detection rate. We also check the sensitivity by increasing and decreasing the foveation given by our prediction. And we also do the experiment on other platforms, and we observe the same trend. In addition to this, we compare our foveation with radially symmetric foveation, which is closer to traditional standard foveated rendering. On desktop, participants over 50% of the time prefer our method, and this looks statistically significant for 4 of the scenes that we tried. On HMD, results are closer to 50%. Our observation is HMDs cannot provide the high resolutions that are available on desktop displays yet. And the land separations prevent people from seeing difference. So both our result and full resolution may look, radially symmetric foveation look very similar. So people cannot see the difference. We also have an implementation for foveated ray tracing. We adjust the amount of rays traced based on our prediction. And we see 15% improvement in the rendering time compared to the standard foveation. So I have another video. So again, this is low resolution rendering, which is the input for our model. Predictions are done on this low resolution. This is the predicted resolution map, and these are additional rays traced in order to increase the resolution in these regions. And this is the final reconstruction. So we perform a performance benchmark. We measure that overhead of running this predictor is 1.2 milliseconds. However, this isn't fully optimized. And we are using 3 different shader complexity levels. The first one uses simple textual lookup. Water and fog are using more complex effects. And we see that full resolution rendering takes almost 23 milliseconds per frame to render in the most complex shader, while standard foveation reduces this to around 14 milliseconds, and ours is around 5.5 milliseconds. We can see that our method is slightly slower in the simplest shader. This is due to the fact that we have this overhead, and the scene is so simple that we need more complexity in the shader to compensate for the overhead spent for making the prediction. So in conclusion, in our work, we provide results of experiments to investigate the visibility of foveation as a function of both eccentricity and underlying luminance contrast. We provide a computational model for predicting the acceptable amount of quality degradation. And we show an application to foveated rendering using NVIDIA variable rate shading. As a future work, our model doesn't optimize rendering costs related to geometry. So, for example, simplifying geometry, that can be another way of implementing foveated rendering. We think that further investigation is required for HMDs, considering the effect of lens distortion or device-specific limitations. And we also we think that it's worth considering to address different foveation parameterizations. So that's the end of my talk. Thank you very much.
So do we have questions? I have a quick question. So for each pixel beyond the color that we have available, there are other information in the rendering pipeline that one could use to predict the importance of the blurring in the degradation of the image quality, such as the material properties that you have behind the pixel.
Mm-hmm.
Did you look into exploiting this
No,
extra knowledge?
No. This is a valuable, it worth considering this as improving this type of foveation. So in order to implement this, perceptual aspects should be evaluated, how visible the distortions are when using these additional effects. We didn't do this, but it's a good suggestion. Thank you.
Thank you. Yes.
Thank you. Very nice work. I have two questions. First is, do you ever encounter a situation where you basically, the whole screens need to render at the full resolution because maybe the contrast is high everywhere? The second is, how did you handle the flicker detection, especially in the periphery? Thank you.
Mm-hmm. The first question, if the scene is a regular scene, it can be like the probability of having a specific type of signal which would require high resolution is very low for natural type of scenes. Therefore, for natural graphics renderings, this is not possible. But if you design an artificial type of signal, like a very high contrast and high frequency signal, you may see such type of behavior. And what was the second question again? Flickering. So this problem applies to both standard foveation and our method. It's not specific to our method. This is why we are using this Gaussian type of filtering, because it simulates proper temporal filtering as well. But this should be a part of, if you reduce the resolution, flickering always occurs. So this should be handled by the renderer or the developer.
Maybe one last quick question.
So my question is about how do you get the patch? I mean, you rely on the rendered scene without actually rendering it. How do you get the patch? And
we are actually rendering the patch in lower resolution. So this is like two-pass rendering.
Okay.
The first one is off-screen rendering for the prediction, on which we are taking patches and making our predictions. In the second pass, we are rendering in using our resolution map.
So given that, the dual pass rendering, if you're like, let's say, vertex shader bound, then you have to pay that penalty twice. Is it possible to use the previous frame? Previously rendered frame?
Yes, that's a good question. Yeah, I think it can be used in order to save time. Some of these steps in rendering pipeline may be optimized.
Thanks.
Okay. Before thanking the speaker, let me complete the author list, because I had only a truncated version for this paper. So the other authors are Marek Wernikowski, Radoslav Mantiuk, Hans-Peter Seidel, Karol Miskowski, and Piotr Didik. And let's thank the speaker again. Okay, the next paper is titled Foveated AR, Dynamically Foveated Augmented Reality Display. The authors are Jong-Yoon Kim, Youngmo Jeong, Michael Stengel, Kan Aksit, Rachel Albert, Ben Boudaoud, Trey Greer, Joanne Kim, Ward Lopez, Alexander Majersik, Peter Shirley, Joseph Spuge, Morgan McGuire, and David Ripke. Quite an impressive list.
Thank you for introducing our long author list. Thank you. Hi, I'm Jong-Young Kim from NVIDIA Research. Today, I'd like to introduce our recent work, Foveated AR, Dynamically Foveated Augmented Reality Display. Let me start with the concept of the Foveated display. The human eye is a really good camera, so the field of view is over 180 degree, and the resolution can be up to 60 cycles per degree, which is 2010 vision. To match the 2010 vision over the whole field of view, we need over 21K pixels for horizontal direction, which is not achievable with current technology. However, human vision has a very interesting visual acuity over field of view. The right graph shows the distribution of cone cells and rod cells in the retina. The cone cells, which is directly related to the resolution, are concentrated in the foveal region and rapidly decreased as it goes to the periphery. So you can know something is in your peripheral vision, but you cannot read the detailed information. Therefore, in the single moment where the user's gaze is at a certain direction, the user cannot perceive all the information at once, even if we can deliver this 21K pixels to the retina. So if we can track the user's gaze and somehow deliver the high-resolution foveal inset display to the fovea by changing the optics, then we can reduce the number of required pixels a lot. And this is called Foveated Display. So many of you should be very familiar with the foveated rendering. However, foveated rendering without the foveated display is just half of the technology. In the display maker's point of view, foveated display can bypass all the complicated problems, including transmission bandwidth, power consumption, and pixel pitch. So foveated rendering should be realized on the foveated display for the best efficiency. So in this work, we presented an AR display which matches the human visual acuity. For foveal vision, we deliver a high-resolution but small field of view display. For peripheral region, we provide a large field of view but low-resolution display. By actively tracking the gaze location, we actively steer the optical path of both displays to always deliver a high-quality image wherever the user is looking at. Our work is the first demonstration of dynamically foveated display in AR format. Our display provides up to 60 cycles per degree resolution to the fovea and 85 by 78 degrees monocular field of view, 12 mm by 8 mm eye box, and varifocal foveal image. We applied corresponding foveated varifocal rendering pipeline too. This video shows the overall shape and the components of the foveated AR display. In Foveal Display, a full HD micro OLED is used. In Purple Display, an HD laser projector is projected into the eye with the lens HOE, which is holographic optical elements. Let me show the Purple Display beam path first. The light rays from the laser projector meet the beam-shaping convex lens, right-angle prism, diffracted by this HOE, and create a Maxwellian viewpoint. Please note that this HOE only reacts to the light from the laser projector and is transparent to the light from the outside. So this is an AR display. Since all the light rays go into the center of the pupil, the displayed image is all in focus. This is the diagram for the foveal display beam path. Light rays from the micro OLED located in front of the forehead is bounced at the half mirror, bounced again at the half mirror image combiner, and then delivered to the user's eye. And this is the gaze tracking beam path. The IR LEDs located on the HOE frames shine some infrared light to the pupil. Then the pupil image is reflected the other side of the half mirror and then goes into the eye tracker. So one nice thing here is that we can actually get the nice on-axis eye image with this configuration, which has better accuracy and robustness compared to the off-axis eye image. Based on the tracked gaze information, the micro OLED and the HOE are actuated simultaneously. Since the required traveling distance was different, we applied double-threaded screw to move both of them correctly. Let me introduce the details one by one. The Foveal Display is a large field of view, all-in-focus, virtual retinal display. We recorded the HOE with 3 color lasers, like the left figure, and then reconstruct them with the laser projector, like the right figure. The eye relief was only 22 millimeters, so we were able to achieve 85 by 78 degrees field of view. Resolution is low, but it is fine because it is periphery. Since all the light rays go into the center of the pupil, and also because the laser projector is used, the image was all in focus. However, the static eye box was really small, around 0.5 millimeter, but we solved this problem by actuating the hologram. So this is how we steer the eye box. First, we projected the image larger than the HOE size. As eye rotates, we move the HOE to that direction and change the input image accordingly. This dynamic eye box concept is not new actually. In last year's SIGGRAPH Asia, Dr. Chang-won Jang proposed a similar steering method by changing the effective light source position using a MEMS mirror. However, we realized that this HOE shift method can achieve larger dynamic eye box compared to the Chang-won's method. This video shows the simulation results directly comparing HOE shift method and the light source shift method. The gray lines show the efficiency of the hologram at a certain point. So especially for the small eye relief and the large field of view, HOE shift method can provide larger eye box, as you can see in the right graph. Foveal Display is a modified birdbath optics. The light rays from the micro display is reflected twice at the half mirror and the half mirror image combiner embedded inside the slab. We can design various resolution Foveal display by changing the curvature of the image combiner and then changing the micro OLED position. We designed 30, 40, and 60 cycles per degree image combiner, which can provide 32, 24, and 16 degree field of view respectively. We can also provide varifocal images by moving the micro display up and down. So the foveated AR is composed of a varifocal foveal display and an all-in-focus peripheral display. It was pretty reasonable choice because the depth information is mostly acquired from the foveal region. We also applied NVIDIA's deep learning-based gaze tracking algorithm called NVGaze, which is published to Saccade this year, so please check the paper for the details. There was a small kick in the image combiner, so I'd like to highlight this. We embedded the half mirror image combiner inside the slab rather than coating the spherical surface. This planar image combiner has a lot of advantages. First, it can achieve shorter focal length because of the refraction. Making a shorter focal length is really helpful for compact near-eye display designs. Second, we can avoid the ghost images. There will be a small refractions, of course, but they are not magnified, so it will be easily blurred away. Last but not least, it looks better than the bug eye structure. So let's see how much this foveated AR can meet the human visual acuity. The x-axis is the angle from the fovea, and the y-axis is the angular resolution of a human and the display. The black line shows the 2020 vision acuity, and the gray line shows the maximum visual acuity of retina, which is 2010 vision. The red dotted line shows the trade-off between the resolution and the field of view of Foveal Display, and the bandwidth is controlled by the pixel numbers. We made 3 different image combiners, and the red boxes show the covered resolution over field of view of each combiner. The blue line is the resolution over field of view of the Perceptual Display. It is pretty low, but it is fine because the human visual acuity is lower than that. So by combining the image combiner 1 and the Perceptual Display, our implemented prototype can barely cover the normal human vision acuity. But the overall coverage can be elevated with the better displays. So without foveation, we need 21K pixels for 180-degree field of view, but with foveation, we need only 4K Foveal Display, 1 Foveal Display, and 1 full HD Perceptual Display at maximum. This is the power of the Fovea Display. So previous slide was for the center gaze, and this slide shows the gaze angle coverage. The left graph shows the required traveling distance for micro OLED and HOV. To cover plus minus 20 degrees, micro OLED should travel 18 millimeter, and HOV should move 6 millimeter. The required distance was different, but the ratio of them is consistent as 3:1. So we can actuate both of them with a single actuator using different gear or double-threaded screws. The right graph shows the angular resolution over gaze angle and eccentricity. Within the plus minus 20-degree gaze angle, the Fovea Display provides Fovea acuity within the angle coverage. So many people ask me about the latency. So can you actually move the optics as fast as your eye? The answer is no and yes. The user's eye just moves first wherever they want to look, and it is super fast. However, when you change your gaze from here to there, your eye doesn't rotate slowly. It moves like here and directly there. So this motion is called saccade. So when you saccade, your brain blocks the information for the very short amount of the time because the information changes too fast. So this graph shows the contrast sensitivity changes over the time when you saccade. So you become completely blind before and after saccade. This is called Psychotic Suppression. So we have this 50 millimeter time slot that we track the new eye position and move the optics accordingly. Since the required traveling distance for HOV was only 6 millimeter, the required speed of the motor was 120 millimeter per second, which is much slower than your eye speed. In addition, the both moving parts are super lightweight too. Micro OLED is 3 gram and HOV was just a film, which makes it more practical. The accuracy and the reproducibility was also really important. All of these conditions were able to be achieved with the servo motor used in the benchtop prototype, but it wasn't feasible with the small stepper used in the wearable prototype. But I believe this is the engineering challenge rather than the theoretical impossibility. This is the benchtop prototype. The Foveal Display moves in 3-dimensional direction, and the Perceptual Display moves in 2-dimensional direction. All the results were captured with this Pixel 2 smartphone camera. Before showing the result images, I'd like to introduce how we calibrated Foveal and Perceptual Display. For the geometric calibration, we captured the checkerboard images for all possible gaze angle and calculated the homography. So if it is the left bottom figure is the target image, the red is the gaze direction, we pre-distorted image accordingly and generate the base images for both displays. And also the blending of transition region is important. When the resolution is changed from a very high fovea to very low periphery at once, it is so noticeable and pretty distracting. So we applied this blending algorithm between fovea and periphery. We linearly increased blur size and slowly mixed the intensity for smooth transition. Finally, the color should be calibrated. Since we used very tricky displays, micro OLED and laser projector, and because of the wavelength selectivity in HOV, the calibration was so difficult. We measured the color primaries and gamma function for all intensity levels and set the new color primaries for the overlapped region in color space and calibrated the color. This somehow worked, but not perfect, so we needed to define a calibration by hand. Let me show the display results. We measure the angular resolution by calculating MTF with the slanted edge method. As expected, the Foveal display provides 30, 40, and 60 cycles per degree MTF 50 value, and Purple display shows lower MTF value, like 3 to 5 cycles per degree at the center. The second is field of view and eyebox. Foveal display is just broadband optics, so the eyebox was huge. The Purple display had a very big field of view, so we had to measure it indirectly from the top view. As you can see, the green HOV only redirects the green light rays from the laser projector and creates a Maximilian viewpoint at the 22mm eye relief. As gaze angle changes, we move the HOV in the same direction. So in the video, the HOV is moving to the right direction, and you can see that the Maximilian viewpoint is also following the HOV and moves accordingly. The overall eyebox was more than 12 millimeters and while preserving the large field of view. So if you overlap 3 different positions here, all of them were pretty large field of view, and the eye relief was remained as 22mm. This is the calibrated results. The geometric calibration, color calibration, and blending algorithm were applied as shown in the figure. This is the moving foveal inset. The high resolution inset is moving and the left object are real objects. The blending algorithm is not applied here, so you can see the sharp transition region here. This is the results with the blending algorithm. You can see much smoother transition in the video. This is the gaze angle coverage result. It is well calibrated from -20 degree to +20 degree, and the foveal image is always located at the center foveal position. The image is located at the real world coordinates, so it is floating there, independent to the camera angle. This is the focus changing experiment. So when we change the camera focus only, the foveal display is blurred while the purple display remains the same. So this shows the all-in focus of the purple display. So by moving the micro display accordingly, we can sweep the focal plane and provide in-focus image for all depths. This is the full color results with the defocus rendering. When you look at the strawberry, you can see the foveated nutrition information of a strawberry. When you change the gaze to the donut, which is located behind, then the nutrition information of donut is in focus, and the strawberry information gets blurry with the strawberry. We also built a wearable prototype. We 3D printed most parts and used a double-threaded thumb screw to move both micro OLED and HOV accordingly. This is the new version with the stepper, and this is the wearable prototype results. When the camera is at the right position, you can see the foveated image with the wearable prototype too. Thank you, everyone. We have all the demos of benchtop of the wearable prototype in the eTech booth, and also the prescription AR prototypes, so please come and check. Thank you. Thank you.
We have time for one quick question. By the way, all the authors will be here right after the last talk if you want to come and discuss with them. All right, I have one simple question. Like, I guess there is some sound or some noise produced by the system. Did you measure that, like on a long session, or does it?
No, actually, the Wearable Prototype has a small sound, but it is so close to the ear, so it is definitely yeah, there. But we didn't care about the sound this time, but I think it is some kind of one of the other engineering challenges if you really want to commercialize this project.
Yeah, please go ahead.
I have a similar question. Isn't like the mechanical part, the stepper motor, introducing some micro vibration that can introduce like blurriness of the image because the whole system can a little shake?
Yes, the vibration is also one problem. So that's why the accuracy, speed, and also the reproducibility is also pretty important. If they are traveling pretty fast enough, and then stay there after the travel, then it's fine because you are actually blind during the saccade. But it is actually related to the motor specification and also the eye tracking the specification too.
Okay, thanks.
Thank you.
All right, let's thank the speaker again. Okay, the last paper of the session is entitled Widgets, Modular Mechanical Widgets for Mobile Devices. The authors are Chang Chiao, Carl Bayer, Chanchi Zheng, and Shri Nayar. And this is Chang who's giving the talk. You can go.
Okay, thanks for the introduction. Today I'm going to introduce our work, Widgets, Modular Mechanical Widget for Mobile Devices. This work is done when I was an intern at Snap. So let's start from taking a look at the evolution of the mobile devices. As we can see here, the screen size is getting larger, while the number of physical buttons on the phone become less. In the latest iPhone 10, they even removed all the buttons on the front screen. Only remains volume button and power button on the side. Apparently, this design are adopted by more and more manufacturers. And thanks to the advanced touchscreen technology, we have greater flexibility to operate our phone compared to the old keyboard one. We all like touch screens. However, there are still some limitations if we use only touch screens. For example, operating the touch screen requires direct contact with human skin. If we are wearing heavy gloves in the winter, then we are unable to operate it. Another limitation is some operation on touch screen requires complex hand gesture. For instance, in a camera app, a zoom-in action can only be triggered by pinch gesture, which is hard to perform when only one hand is available. Imagine your other hand is holding a cup of coffee or something else. Moreover, a touch screen is a device serves as not only as an input panel, but as a display. This means that if you are using your phone, certain visual content would be unavoidably occluded by your finger. In addition, we humans are very touchy and feely. We want to not just know what we have touched something, we would also like to have a confirmation of something that has happened. In other words, we appreciate tactile feedback. However, the virtual touchscreen button provides no this kind of feedback. Based on those limitations, we want to ask a question that, should we bring buttons back to our phones? Well, we definitely don't want to go back to the old era to use a phone which contains a keyboard and full of buttons. It is not only because it has a very small screen-to-body ratio, but also there might have some capability issues, because the modern operating system is not designed for those kind of phones. Some companies have designed game controllers for mobile devices, which are getting popular in recent years. However, those game controllers require either wired or Bluetooth connection. Thus, it needs both hardware and software support. Also, it is usually bulky and inconvenient to carry out. There are also some research work that enable tactile buttons on a mobile device. Savage and colleagues use 3D printed input devices. It generates time strike sound by moving its interaction component. Then a real-time audio processing pipeline analyzes the resultant sound to recognize the interaction event. However, the 3D printed input device is bulky, and it requires an external microphone attached on the mobile phone. Laput and colleagues proposed another acoustic-driven interaction method. In this method, they connect the phone's microphone and its speaker by a soft tube, and let the speaker generate ultrasound wave constantly. By pressing the soft tube, its acoustic property will be changed, resulting in a change of the received signal on the microphone. But this method requires the speaker and microphone turned on at all times, which is very power-consuming. Recently, Strasnik and colleagues invented a system which actuates physical controls around the edge of a mobile device using magnetic local motion. However, it designed a complex circuit and again made the system too bulky. Based on those previous designs, if we really want to bring buttons back, there are several issues we need to address. The first one is the button must have a small form factor. Introducing the button to the phone will not increase this physical size too much. Second, it must be compatible with the modern mobile operating system. Also, we want it to consume minimum amount of power, or even no power. Lastly, we want to keep the manufacturing cost as low as possible. To build an input device that satisfies all these conditions, let's first take a look at how does a mechanical button work. This is a mechanical button widely used in computer keyboard decades ago, called the buckling spring button. When we press the button, as we press it deeper, the required force first increases. At some point, the internal spring buckles and the force drops suddenly. The relationship between the pressing force and the pressing depth of the button is called the force displacement curve of the button. And the turning point is called the actuation point, where our fingers start to feel tactile feedback. A similar mechanism is also used in the button on the phone. Instead of using a spring, those buttons usually use a membrane. For the purpose of discussion, let's imagine that you are holding your phone and press the side button. When you press it, you can feel a click. And this click will result in a very subtle motion of the phone. The reason of this subtle motion is when we hold the phone still, our finger force applied on the phone balance each other. When the button is being pressed, its resistance force increases, so does the finger pressing force. At the moment where the actuation point reached, the resistance force of the button drops largely and suddenly. In a short period, the total force applied on the phone becomes imbalanced and causes the phone to shake. A very important observation is, although this shift is very subtle, the motion signal can be captured by the accelerometer, or the IMU, in the phone. The IMU measures the acceleration on 3 axes with respect to the phone's local frame, and it is available not only on the mobile device, but also other wearable devices such as smartwatch. It is very power efficient and always turned on. Here is how the 3-axis IMU signal looks like when we press the side button of an iPhone. As we see here, when the button goes through the actuation point, a strong motion signal captured by the IMU. Notice this is irrelevant to any electronic connection between the button and the phone. In other words, by barely analyzing the IMU signal, we should be able to recognize this pressing event. Now, if we are able to make more this kind of button and attach them to the phone without any electronic connection, we can press these buttons and talk to the mobile device just through the channel of IMU signal. This is the basic idea of our vibration-based input, which we refer as wedges. So how to design wedges? As we discussed before, to create a subtle motion that can be captured by the accelerometer, we need a sudden force drop during the pressing. Instead of using a buckling spring, we propose to use the spring ball model. When pressing, the contact force between the teeth and the ball will first increase due to the compression of spring. At the point the teeth pass through the ball, the contact force changes direction suddenly, resulting in a large force drop of the required pressing force. The spring and steel ball can be purchased from regular hardware stores. The button and the shell can be produced by 3D printing. Therefore, it has a very low cost, approximately 50 cents. Also, it can be made very small, as shown here on the right. Similarly, a rotary knob can be designed using the same spring ball model. To quantitatively analyze the behavior of our system, we build a force model. Consider the process that a button is being pressed. We assume that total force applied on each component is balanced. If the force on the button is balanced, we will get our first equation. Here, Fp is the force exerted from our finger. F2 is the spring force on the button. Fb is the contact force. Alpha is the contact angle between the teeth and the ball. And mu is the friction coefficient. Similarly, if the force on the ball is balanced, we will get another equation. By solving these two equations, we will get this relationship. It shows how the finger force would change when the contact angle alpha is changing. And if we know the exact shape of the contact teeth, we can compute alpha at every location. Thus, Fp is known everywhere. So we have the quantitative relationship between the pressing force and pressing depth, which is the force displacement curve. Using this force model, we can design different teeth geometry to see how the force displacement curve would change. As we can see here, different shape of teeth will give different force displacement curve. We found that from different force displacement curve, we will get different IMU signal. Besides changing the shape of the teeth, we can also change the physical parameter of the system. For instance, we can change the spring constant of the ball spring, or the spring constant of the button spring, or even the ball radius. By playing with those physical parameters, our system gives us a lots of flexibility to produce distinct IMU signals. We now have a basic design of the wedges. So the next question is where to put them. Since wedges are small, one simple solution would be attaching them to the phone case. A recent survey shows that there are more than 80% of people use phone case to protect their phone. The phone case offers a natural real estate where the widget can be attached as individual modules. Also, another benefit is that the attached widget can be reconfigured to fit customized preference. Here we show the real-time IMU signal. As we can see here, the interaction event creates very strong signal. Now we are able to create strong signal by using widgets. But if we have multiple widgets on a phone, how can the phone recognize which widget is being interacted? Before we dive into the recognition algorithm, let's think a bit about what requirements should these algorithms satisfy. We found that different people will create a slightly different signal even for the same widgets, mainly because they have different ways to hold the phone. So we must have a calibration step before the usage. This must be very simple and requires minimum effort for the user. Also, since this is for user interaction, the delay caused by the recognition must be very short, at most 100 milliseconds. So the algorithm must be lightweight. We cannot use heavy deep learning algorithm for recognition. Here we present a simple yet powerful algorithm for our detection. We first pass the signal through a high-pass filter, which removes most of the low-frequency environmental noise. Then we plot the square value of the filtered signal, resulting in an energy plot. We extract the local maximum of the energy plot and remove the maximum point that is too close to each other through the non-maximum suppression. The remaining points indicate the time step of a potential widget interaction event. Then we let the detected significant point be the center and segment the signal using a 50 millisecond window. As we mentioned before, we ask the user to perform a simple calibration step before his first-time usage. The calibration step asks user to interact with each widget 5 times. Using the same segmentation algorithm I just described, the segmented signal is stored for later recognition usage. The calibration takes only a few seconds and only need to be performed at the first time usage. Let's go back to the recognition algorithm. After we detect the significant points, we get several signal segments that is potentially our widget interaction event. Then we run KNN matching under the dynamic time warping metric to match between the segmented signal and stored training signal. If the matched distance is larger than a threshold, we just discard the segment and treat it as noise. Here we show our experiment's results. We recruit 13 participants to evaluate our system. The experiment asks the user to interact with each widget 30 times and to see if our algorithm successfully recognizes which widget is being interacted at each time. We found that if all 8 widgets are in use, we achieve 93% accuracy. If we remove some of the widgets, the accuracy is even higher. For example, this 5-widget layout gives us a system that has 97% accuracy. For the details of our experiment, please refer to the paper. Last, let's take a look at the application of widgets. As we mentioned, using a touch screen with glove is inconvenient. Some simple operations, such as answering a phone call, can be easily implemented by our system. Some operation like camera zoom is usually hard to perform when only one hand is available. By using widget, this operation can be easily achieved using only a single hand. And the configuration can be easily changed to adapt a left-handed person. Our system is also very robust. The environment noise cannot trigger the recognition system. Mobile gaming is another limitation of touchscreen interaction. By using widgets, the gaming experience becomes more natural and similar to use a game controller. Last, we demonstrate a virtual saxophone implemented by widgets. The microphone inside the phone picks up the blowing sound from our mouth and produces sound based on the key combination of widgets. Our method also has some limitations. Theoretically, our method cannot handle simultaneous input. However, we found that in practice, even when we intend to press 2 buttons simultaneously, we can still able to observe 2 click signal in a very short time interval. Thus, it is possible that we can still recognize simultaneous widget events. Also, we found that our recognition accuracy will decrease if we operate widget in a dynamic environment, such as on a running train or car. This is mainly because the calibration is performed in a static environment, and the environment motion will add lots of noise to the detected signal. To conclude, we create a set of modular mechanical widgets that use the IMU signal to communicate with with mobile devices. It requires no power consumption or electric connection. It is low cost and has small form factor. It allows the user to build a customized user interface and provides tangible feedback. And this ends my talk. Thanks for your attention.
Do we have questions? Yeah.
Hi, it's Jenny from New York University. Very interesting and helpful work. So first question is that I think I might miss some part, that how could you connect your mechanical buttons or rotational wheels to the IMU signals?
We don't need any electronic connection. So basically, we just we 3D printed some phone case, and the phone case has some slots. We just attach the widgets into the slots, and when we press this button, they will create this create a subtle vibration that can be captured by the IMU.
Oh, nice. Yeah, I originally was thinking about Bluetooth signals, but you already mentioned in the beginning that you don't really want that happen. You want to use some other signals. Yeah. And the second question is that, well, when you are really using these mechanical widgets, we cannot see any hints from the phone screen itself. So it's like we need to memorize it by our own. That okay, if I press this button, then I want to shoot during this game. Yeah. So I'm not sure, but it's a very minimal suggestion that if we can have some hint in the UI or floating hints, floating UI, so that people knows, okay, if I really want to play this game, I want to take a photo or take a video or zoom in, zoom out, I need to use this specific button instead of other buttons because we can have 8 slots there.
Yeah. So actually, so first we need software support for this widget to use, and the software can be written by any people, so they can design what kind of user interface that can provide some hint. Yeah.
And have you tried to combine 2 widgets at the same time, like press 2 buttons?
Yeah, as I mentioned before, the widget, theoretically, we cannot handle simultaneous input. But however, we found that even when you intend to press 2 buttons simultaneously, there's still some time interval between these 2 clicks. So it's possible that we can do this press simultaneously.
Thank you very much. I really like the sex part.
Thank you.
Hi, Felix here from Princeton University. Really enjoyed the talk. It's an interesting take on the problem.
Thank you.
So you had mentioned before that one of the benefits of this method is how configurable it is. You can reconfigure.
Yeah.
But I would imagine, let's say you had an actuator on the right side and then move to the left side, you'd have to recalibrate. Does that mean every single time after this sort of reconfiguration, you'd have to rerun these calibration steps?
So basically, if you let's imagine you have only a few buttons. Actually, you can do a calibration at the very first beginning. You want to, for example, you want to do the left-handed person and the right-handed person. They can actually do the calibration together. And whenever they want to switch, they just switch the button and they can use later. Yeah.
Okay. Yeah.
Yeah, but if you have lots of buttons and you want to reconfigure that, a better way to increase the accuracy is to do the calibration every time you use it. Yeah.
And one other thing, let's say you have 2 actuators on one side. It seems like the motion that would come from that, the readings would actually be relatively similar. Did you ever run into any problems regarding that?
So basically, we have multiple physical parameters or the shape of the teeth to control the signal. We found that if we make, for example, if we make the physical parameter or the shape of the teeth very different, the signal will be very distinct and they will not confuse together.
Great. Thank you very much.
Thank you.
one very last question.
Hello, Shutong from University of Maryland. Thank you very much for this presentation. Very awesome work. I just imagine that using the IMU will require some energy. So did you measure it so that you know the amount is actually negligible, or maybe the modern phone architecture just have IMUs on all the time?
So from the Android document, they said the IMU is running all the time. So in our system, we actually don't require extra power consumption because the IMU is always down there, and we just read the signal from the IMU.
I see. Thank you for the clarification.
Thank you.
All right, let's thank all the speakers again. Bye-bye, everyone.